In order to achieve synchronization of power electronics to the grid, we have two different options. The first one, what we usually refer to as grid feeding or grid following converters, is the most commonly used for IBRs. These systems require a phase-locked loop or PLL for synchronization, and they also require a reference from the grid. That means we need to have a voltage at its output for which this converter can synchronize to. The biggest problem is that when we connect this converter to weak grids, we tend to have quite a lot of issues. The second option, which we will explore later, is what we call grid-forming converters. These systems are self-synchronizing, they are better suited to weak grids, and they can emulate the inertial response of a synchronous generator if we want to achieve this kind of functionalities. The most critical part of synchronizing the grid-following converter to the grid is what we refer to as the phase-locked loop or PLL. This, using local measurements, generates the reference that the converter can synchronize to, and it enables us to implement the rest of the control functions. The main function of a grid-following converter is to feed power into the grid, directly controlling the current that flows from the terminals back to the rest of the power system. The output of the phase-locked loop, or PLL, is instrumental in achieving synchronization with the grid for power electronics converters. If everything in our grid is nice and smooth, then we do not have any issues with tracking that particular reference, and our synchronization is very straightforward. However, our grids are becoming weaker and weaker, and with these changes, we start seeing issues with our synchronization. For example, during transients, or when we have a grid with substantial distortion or harmonics. I did mention that most of the difficulties for grid-following converters appear when our system is becoming weaker. What does that mean, though? Traditionally, system strength has been quantified through fault current level calculations, with AIMO's definition giving us some indication of what to expect in strong and what to expect in weak grids. As a very local example, we can look at the West Murray zone in northwest Victoria. In this area, due to the remoteness from synchronous generation and with the many new IBR plants, we have observed multiple instances of oscillations that can be directly attributed to the weakness of the grid. The weakness is enough that AIMO clearly sets the need for advanced tools and methods that will allow us to understand and interpret the system interactions in this area. The weakness of the grid is enough that AIMO clearly sets the need for advanced tools and methods that will allow us to understand and interpret the system interactions in this area. These are issues that we face today, and we expect to get worse as we remove more and more synchronous generation from the system. In this map, the red dots represent areas that we expect to observe issues related with system strength, and as we move towards higher proportion of renewables to 2050 and beyond, we see things getting worse and worse. As we integrate more IBRs into our power system, we need to take a more holistic view of how we even define system strength. For example, if our converters are unable to ride through faults, which may lead to malfunction of protection equipment, we are concerned about voltage stability. So we really need to think, does the system have enough fault level available at the current location? When we experience wide area undamped voltage or power oscillations, we need to look into the small signal stability of our system. This means we need to understand whether the system has enough impedance for our converters to not experience any of these instabilities. And as we see higher rate of change of frequency, it will take longer time for the power system to recover after any events or any oscillations, which makes us concerned about frequency stability. So we really need to answer, does the system have enough inertia? This means that in a power system with high penetration of IBRs, we cannot really separate inertia from system strength. We need to consider different aspects simultaneously in order to achieve a secure operation of an IBR-dominated power system. To compound on this issue, grid-following converters based on PLLs have additional issues, as the mere injection of their own power into a weak grid has the potential to distort the grid and destabilize their own operation. We do not have a need for external disturbances to observe issues with these inverters in a weak grid.